Hello, everyone, and welcome back to Teach Astronomy. My name is Victoria, and I'm here with Professor Chris Impey, and we're doing a astronomy Q&A live stream today, answering all your questions about astronomy and astrophysics and space science. And I am filling in for Matthew today, so I will be asking the questions. So feel free to start posting those questions in the chat, and we will jump into it. While we wait for people to join us, Chris, did you want to do a little introduction of yourself?
Sure. So welcome everyone for the live session, typically for people in our online classes. We're now 4 different online classes, or you may have just found this by another means. It doesn't matter how you found us, welcome. Floor is open for questions about pretty much any topic in astronomy.
All right. So as you guys start to ask your questions, I thought we could start with a little bit of, current events. So Professor Impey, the other day, SpaceX had a launch, and it did what they call a rapid unplanned disassembly, as they say in the business. Did you want to talk a little bit about that whole thing and how that might how some of these SpaceX launches going bad affect space travel in general?
Sure. So the larger picture here is that SpaceX has generally been extremely successful in the last few years. Their workhorse rocket, the Falcon 9, has had, I think, over 120 successful launches, maybe with one failure, but with almost no failure. So it's extremely reliable. The new rocket is called Starship. It's extremely ambitious because it's essentially takes the same rocket engine that is used in the Falcon 9 and puts 33 of them behind one rocket. Now that's an interesting choice because, of course, Saturn V you had a much smaller number of very powerful engines, and they've just taken a modest engine and put a lot of them behind one rocket. And as we learned, a number of them, I think 8 or 9, according to reports, malfunctioned or failed. And that's quite a large fraction of 33. So obviously the rocket became unstable, and it started pivoting and spiraling and eventually combusted and blew up, essentially. So that sounds like a pretty bad failure to most people, but Elon Musk has a different attitude. He likes to develop fast and break things and then learn from the failures. Sort of the flip side of NASA's approach, which is to be essentially very risk averse and not take chances at all. He's painting this as a success, of course, because he cleared the launch pad, because they're going to learn from the failure, and they'll be back in a couple of months with a new plan for the Starship. Now, some people might think that destroying a rocket of this size and scale, bigger, more powerful than Apollo 5, would be, an expensive and a big problem, but he's gearing up for mass production of the Starship. So his visions and dreams of going to Moon and Mars, and colonizing those places really depends on having a pretty large fleet of Starships. So it's not just that the rocket itself and its boosters are reusable, but he's also trying to scale up the production of these Starships so the unit cost of a Starship goes down. And if he's looking at that long view, then losing a couple of Starships to catastrophes during the testing phase is probably not a big deal, just a bump in the road. At least that's the way he's painting it. So we don't think that this is going to slow things down. Obviously, NASA is eventually partnering with SpaceX and going to put astronauts on board these Starships. And you can bet that NASA's not going to be happy with the Starship with humans aboard that they're party to until it's proven itself pretty extensively. So that's probably a few years away.
All right. And Papas to Pastor actually has a follow-up question to this whole SpaceX conversation. He was wondering, would we have learned anything differently if the rocket fell to Earth without exploding, if it could do that?
Well, it was due to do a sort of near orbit of the Earth and then come down in the ocean, safely in the ocean, but it would have still have been lost. So this was an expendable vehicle, whether it exploded or just fell into the ocean. If it had had a fully successful flight and then landed in the ocean, they would, of course, learn a lot too, and in the end, a lot more, because you just have more data when the rocket is able to fly at high altitude and under under different conditions. So, you can't paint this as a success generally because it wasn't what they had planned to do. They do need to gather data because these engines are extremely high powered. They're under enormous amount of stresses when they do this work. They're in close proximity to each other, so there's sort of vibration effects of the whole thing, and leaks, of course, which are the bane of all rocket engineers' lives and have caused disasters in the past, tend to happen the more plumbing you have, and 33 engines implies a lot of liquid fueled plumbing. So it's almost inevitable that you're going to have problems with a rocket this sophisticated.
All right. The next question is from Yang. If matter is deprived of electrons and positrons, is that technically what dark matter is? And if so, can EM waves have different speeds, and can they be compounded into hadron pairs?
So being deprived of electrons or positrons, dark matter, as far as we know, and we don't really know a lot about dark matter. Dark matter has a very weak interaction with the electromagnetic force. So with free electrons or positrons, charged particles, it does not have interactions with those particles, nor any particle that's subject to the electromagnetic force. And that's pretty much all we know. That's a sort of null of dark matter, that it doesn't interact that way. All we found is that it interacts gravitationally, and the particle is being searched for on the basis of mechanical collisions in deep mine detectors, typically. So it can be detected, of course, and mapped by its gravity. That's what astronomers do. But physicists are going to try and detect the fundamental particle that we think is the dark matter entity by essentially resonance in a solid state detector and the very rare collisions where you capture the energy of the collision in terms of basically sound waves in the substrate.
All right. Next question is from GeoSpacePad. They're wondering, does the solar wind ever speed up or slow down the rotation of the sun?
That's a good question. The sun is a rotating object, has angular momentum. The solar wind is a stream of high energy radiation and particles leaving the sun. And so, yes, in principle, by conservation of angular momentum, if the sun is losing mass and energy through the solar wind, then it's also losing angular momentum. The thing is, however, that as impactful as these particles and that radiation is to the Earth and to our telecommunications and so on, they are a truly negligible fraction of the sun's mass. So it's not like the sun is losing any kind of significant mass this way. It's such an unmeasurable amount, essentially. So there's no way we'd see the effect on the angular momentum.
I think I was still muted there. Sorry about that.
Yep.
The next question comes from Jerry. He was wondering, can you talk a bit about the composition of the fabric of space-time versus the matter that occupies it? And what is the nature of the fabric woven into the vacuum and matter?
So when people talk about the fabric of space-time, that's obviously a metaphor because there's no fabric involved. It's not cloth of any kind. Really, to a physicist, and in terms of the general theory of relativity, what space-time is a manifold. Now, manifold is a purely mathematical term, and essentially the mathematics of general relativity defines space-time in that way, as a mathematical entity that has curvature, but that doesn't actually have any fabric, any essence, any matter content to it. It's essentially a backdrop, but it has geometry, of course. Now, the geometry of space-time is impacted by mass and energy. That's what general relativity says. So we have to separate out the substrate, the backdrop, the space-time itself, a mathematical manifold, from how it behaves with mass and energy in it. And general relativity describes how mass and energy bend space and time, where mass and energy are hyphenated and related, and space and time are hyphenated and related. And that's essentially what the theory of gravity does.
Okay. Next question is actually going to be from last time, last stream. Also, feel free to keep asking your questions in chat, folks. But one of the viewers last time asked, can it be possible for one nebula to have multiple solar systems? And I don't believe we got to that question last time.
Right. Absolutely. I mean, a nebula is just a large glowing amount of gas in the universe, and the gas is glowing because it's lit up by stars within it. And typically a nebula is much larger than a solar system or an individual star system. And so the nebula can be lit up by many stars, and those stars are likely to have planets. And so yes, nebulae can contain many solar systems. The Orion Nebula is a good example. That's a star-forming region that's visible to the naked eye, and is about 1,500 light years away. And that Orion Nebula has a dense star cluster, mostly obscured by dust, at the center, which probably has hundreds or a few thousand stars. And most of those statistically are going to have planets. So yes, many exoplanets and planetary systems within a single nebula is possible.
Very cool. All right. Next question is also going to be from one that we didn't get to last time. Adwaith, one of our regular viewers, had been wondering, what are some of the most significant unanswered questions in cosmology today, in your opinion, and how do you think we might be able to address them in the future?
So cosmology's unanswered questions center pretty much entirely on dark matter and dark energy, since they are the two biggest, most ubiquitous components of the universe, and their physical nature is still unknown. Those are the biggest issues of cosmology. We don't think those entities are going to go away. We have reasons to believe that dark matter exists and dark energy exists, but understanding their physical nature is the goal of cosmology. We can expect good progress on dark matter in the next 3 to 5, maybe 7 years, because the constraints that are coming from physics experiments are either going to find it in terms of a new subatomic particle, perhaps the lightest supersymmetric stable particle out of grand unified theories, or they're going to fail to find it, in which case there's a crisis in physics as well as in cosmology. Dark energy is far less clear how much progress can be made on that same time frame. And that's because our handles on dark energy are very limited. It was detected or discovered through the accelerating expansion of the universe, and really we still haven't found many ways to characterize it other than mapping accelerating expansion in different directions and at different times in the history of the universe. Physics theory is trying to work on the dark energy problem, but there's no unique solution or compelling theory at the moment. So it's possible that time may go by and we still may not learn more about dark energy.
All right. We've got some questions from chat now. Ghost 180 was wondering, they said, even after looking on Google, they're still confused about the shape of the universe. Shouldn't it be a sphere? And why do some people talk about it like a cylinder? You talk about different theories on the shape of the universe?
So there are various theories or hypotheses about the shape of the universe, but the simple answer to the question is the universe is flat. So we have mapped out space-time from radiation that's traveled through almost the entire history of the universe. That's a microwave background radiation. And the way that radiation travels from the time it was released, 400,000 years after the Big Bang, across all the space and time it travels to reach our telescopes, can tell us about the geometry of space. Essentially, those speckles in the microwave background radiation are either magnified or demagnified if space is negatively or positively curved. In fact, we see no magnification of those spots or demagnification. And so actually to within 1%, space-time is flat. And so we're saying three-dimensional space-time is flat. That's the shape of the universe out to the limit of our vision. And that's the simple answer to the question. Now, the only door that's left open by that is the possibility that on scales much larger than our horizon, which is about 39 billion light years in any direction, it's possible there's curvature on even larger scales. So you could have a small region of a sphere that you're looking at that essentially seems to be flat, just as we go out on the surface of the Earth and the area around us seems flat, when in fact the totality of the space-time is curved like a sphere or a cylinder. So that means if the universe is curved, it's curved on a much larger scale than tens of billions of light years. And we don't really have any way to comment on that at the moment because we're limited by what we can see in the time that it's taken light to reach us in 14 billion years.
All right. Next question is from Lauren Secker. Hi, Professor. Do black holes generate heat? If so, how does thermal radiation escape a black hole? And do black holes violate the law of entropy?
Black holes do generate heat if Hawking's theories are correct. His theory hypothesized a very feeble form of radiation that emits from the surface of a black hole. And I think the temperature of it for a solar mass black hole is a few billionth of a Kelvin. So that's an incredibly feeble amount of heat, exceptionally low temperature. It's just an undetectably low temperature. So astronomers are not sure how they will ever detect it. In terms of entropy, the entropy of a black hole is very large. If you do the math, the entropy of a black hole, the mass of the sun, is about 100 million times higher than the sun itself. So black holes do contain and embody very large amounts of entropy. And that's just a referring in the physics definition that where entropy is the number of equivalent microscopic states, that we have to imagine a black hole could have been made any number of ways. And so it has a huge number of possible equivalent microscopic states inside, and therefore it has a large entropy.
All right. Next question is from another one from Papas to Pastor. They said, there is a moon pope, in quotes, and various corporations and countries working on establishing bases on the moon. Do current non-aggression space laws apply to the moon, Mars, etc.?
Space law is actually very underdeveloped just when it comes to things outside beyond the Earth. There have only been 2 UN treaties that relate to space law or ownership or rights, and they're the Outer Space Treaty of 1965, which sort of banned weapons in space. That's a very important thing, trying to demilitarize near-Earth orbit. And then the Moon Treaty of 1979, which did speak to the ownership of space resources. It wasn't signed by most of the world's superpowers, and certainly the spacefaring nations. So there is no current legal apparatus for dealing with disputes about ownership of objects in space or the resources that they might hold that might have value. So it's a bit of a problem. It's a Wild West. And that means when countries start building bases on the moon and Mars, they will, hopefully these are big enough places, they're not going to tread on each other's toes, but there could be conflicts that arise from that, and that has some people pretty worried.
Very interesting. All right. Next question is from Prab. In any star, that may be binary system, is there any possibility to get 2 identical planets where life is evolving?
In principle, it's possible, but in practice, it's not really going to happen because you will never get 2 identical planets in a single star system, because first, you will never, by normal formation processes, get 2 planets that share an orbit and therefore have the same distance from their star. So you can't have twin planets orbiting in the same orbit. And if you have similar massed or sized planets in different orbits, then they'll have different temperatures because they'll be at different distances. So in practical terms, no, you can't really have twin planets in a solar system.
All right. The next question is actually from an email. Also, if you guys are interested in emailing us, I will put the email in chat. From Christina. She asked, since metals condensed first and close to the sun in the solar nebula, Why is metal also a part of the core of ice giants and faraway comets and asteroids?
Well, the heavy elements were available throughout the solar nebula. So as the solar nebula condensed, and there are, of course, there were different temperatures at which things would condense out. Those metals were available throughout the solar nebula. They were just dominated in the outer regions of the solar system by light elements and volatile gases. So we do know there are rocky cores to all the giant planets, and those rocky cores include some metals. So the formation process occurred such that metallic compounds exist throughout the nebula and throughout at all distances from the sun.
All right. Rajat Nano, a viewer, asks, space research helps technological development. So how does the study of extreme environments or the study of astrobiology help mankind?
Astrobiology is not directly helpful to mankind. It's an intellectual pursuit, a curiosity-driven activity to try and see if we're alone in the universe. However, finding other forms of life, finding alternative versions of biology or variations in our biology is undoubtedly going to be helpful in terms of understanding our biology and how to work with biology and maybe with diseases and medicine, because we can only learn about organisms we share the planet with. To find a whole nother set of organisms, we're undoubtedly going to see biological models that will be of interest and perhaps of use to us, where we can co-opt some of their strategies, learn some of their tricks, use some of the pathways and the proteins and the mechanisms they use. So that's an optimistic reading, but that would be one of the hopes of astrobiology.
All right. Pandora Light 24 was wondering about kind of the composition of the universe, and how in the last like a decade or so it's been discovered that the universe is just a lot more crowded than we originally thought. And they were wondering how important is that to, I guess, other theories about the universe and about cosmology.
So the universe may seem crowded when we talk about all the objects and all the galaxies and all the different phenomena, but actually it's a very empty place. The average density of matter in the universe overall is about 1 atom, which is a hydrogen atom, so a proton per cubic meter. That's very, very incredibly good vacuum. The air you're breathing is 10 billion atoms per cubic meter. So this is fantastically good vacuum. So space is mostly empty. The universe is mostly empty. And the objects we know of, which are a large number, hundreds of billions of galaxies, are distributed over vast regions of space. So I would not really call the universe crowded, but the reach of our telescopes is such that we can study objects throughout space and time, and so we have enormous numbers of them in catalogs.
All right. The next question comes from an email from Wendy Traver. Wendy was wondering, when the field of the Higgs boson turned on, could it have given rise to the brief period of inflation in the very earliest microseconds of the cosmos?
So the Higgs field is an interesting phenomenon. It is part of the standard model of particle physics, and it does not seem to have the same physical basis or properties to what's called the inflaton field, which would be the field that might have led to inflation. The inflationary field, the field that spawned an exponentially expanding space-time, is associated with grand unification, we think. The Higgs field does not rely on grand unification theories. You don't have to go to those energies to manifest the Higgs field. So it does seem like the Higgs field is not really going to help us understand inflation.
All right. Next question is from Papas to Pastor. Why can't we have 2 planets that share the same orbit?
That's a good question. It seemed like you might be able to. The real reason is that it would require very particular circumstances to set that up. If we just think about how planets formed in a condensing solar nebula from small objects, originally gas, then dust particles. And then collisions and accretion cause these objects to grow. And the mechanism is typically that the winner takes all. That's the best way to think about it. So as objects form in rings, essentially, around a central star and stick together by accretion and grow in size from boulders to mountains to moons to planets, it's likely that one object is going to have the dominant gravity, and that gravity will then overwhelm the gravity of other objects, and they will stick to it, and so you'll grow one planet. The odds of a stable situation where you have two equal-size objects that have been competing with each other to grow and end up in a sort of standoff of equal size, that's essentially very, very unlikely because it's a highly specialized condition. So basically, for that reason, twin planets in an orbit are simply not going to happen.
All right. We have some more planetary questions and theoretical things. So Ghost 180 said, I'm trying to world build for a book that I want to write. I was wondering if it would be possible for a moon and a planet to share an atmosphere. And if not, would there be a way to build like a pipeline of some sort between them to mix the two atmospheres or create an artificially shared atmosphere?
So it's an interesting hypothesis to imagine, could a moon and a planet share an atmosphere? I think the practical answer for various physics reasons is no. And it really comes down to two things. It comes down to the fact that moons typically are never in very tight orbits of the planets. So you can imagine a moon in a very, very close, tight orbit where a big puffy atmosphere would sort of envelop it and contain it. But of course, if that happened, then the drag on the moon would cause it to plunge into the planet. So even hypothesizing that shared orbit would not work. But in practical terms, moons are in much larger orbits than the planet's size, and so they're much further away than the planet atmosphere can extend. And then it isn't possible to have a super extended planetary atmosphere where it fades off slowly into space, and perhaps the moon can pass through that atmosphere. Because the gravity of any kind of significant sized planet will pull the atmosphere very close. The Earth's atmosphere, if you're using an analogy of an apple, is no thicker than the skin on the apple. So the atmospheres around planets are almost never very extended.
All right. Eudora has kind of a philosophical question, I guess, but also a technical question. They're wondering, do we always study our universe in its past?
Yes, we always study the universe as it was because of light travel time. So if light speed were instantaneous, if it were infinite, which is a thought experiment we can do, it's not the way physics is arranged, but we can imagine it, then we would see the entire universe as it is now. There would be no history, basically. We'd just see everything. It would all be visible to us, and the light would come to us and arrive simultaneously, regardless of distance. But it doesn't. Light travels at a finite speed, 300,000 kilometers per second, and because of the vast distances in the universe, that means that light has traveled substantial amounts of time, millions of years from the nearest galaxies and billions of years from the most distant galaxies. So light travel time, I would prefer to think of it as a feature rather than a bug of the universe, allows telescopes to be time machines and let us look into the past. But it's an irreducible feature of our universe, given that light speed is finite and that the universe is very large.
All right. Next question is from Ravi from an email. They asked, so there's a calculation that we should see approximately one supernova per century in the Milky Way, although we haven't seen one in over 400 years. So is this calculation for the entire galaxy or just the part that's accessible to us from the Earth?
No, that's a good question. The calculation is for the entire galaxy. The average supernova rate in a galaxy the size of the Milky Way is roughly one per century. Now, I've seen theoretical papers where the prediction of that number, the estimate of that number, does vary by a factor of 2. So it's not a hard and fast round number, 1 per century. But that's what most of the studies say. And indeed, we haven't had a supernova in our galaxy since Kepler's supernova 1604, over 4 centuries. So we're due. But remember, these are random events, and so they obey Poisson statistics. And if you ask what are the odds when you have an event that occurs once a century that's dictated by random Poisson statistics of waiting 4 centuries before something happens, the odds, it's a smallish number, but it's not a very small number. That's a few percent, maybe 5, 10%, I can't remember. So it's not implausible. It doesn't mean the calculations are wrong. It does mean we're due, and so we have been due, of course, for a while. And it's possible that the supernova that goes off could occur on the far side of the galaxy from us, and would then be obscured, would be faint because the far side of the galaxy is 50 to 100,000 light years away, and it will be obscured by dust. And so there are certainly big chunks of the galaxy where if that supernova did go off, we wouldn't see it.
All right. And I actually kind of have a bit of a follow-up question to that. I was curious. So, like you said, if it's on the far side of the galaxy, if a supernova goes off, we may not see it. So what would you say is like as far as the telescopes we have here on Earth and in space, is it likely that, if it would be visible somewhere on Earth, that we would see it? Do we have that kind of full coverage almost? Or is there a chance we might miss it?
Because we're not looking hard enough from the Earth? Or because it goes off?
Or maybe just because, a lot of telescopes are looking, if they're looking deeper, like something like James Webb, if they're just turned the wrong way, like if, I know there are some survey telescopes, but is it possible that we wouldn't see it?
I think we would see it because, well, if it's in the nearby part of the galaxy, we would see it. I mean, it could be a naked eye object if it goes off within 100 light years, which is unlikely. That's a small fraction of the galaxy. But there are enough all-sky monitoring systems, not of great sensitivity. The big telescopes like James Webb and Hubble look at small patches of the sky, so they're not going to see. They will miss something because they're not doing surveys. But we do have all-sky monitoring such as to pick out a supernova. For instance, there are X-ray telescopes that are looking at the whole sky, and supernovae will go off in X-rays. And actually, X-rays is a better way to see the ones on the far side of the galaxy because the galaxy doesn't obscure X-rays the same as it does visible light.
Very cool. Thank you. Next question is from Pandora Light. So with James Webb discovering exoplanets, is it realistic to, discover them, as in get to them in the next 50 years with technology innovation, or do any other sort of, I guess just how advanced do you think in the next 50 years would our ability to study exoplanets become? Because right now we seem to only be able to look at them.
Right. And James Webb, just to clarify, is not really discovering exoplanets. That's not its job. It's other telescopes like Kepler and its successor TESS and other ground-based surveys that are finding new exoplanets. James Webb is following up, is pursuing planets that have been found by other means to try and characterize them in detail. As for where we might get to in the next 50 years, the number of exoplanets is due to increase substantially just with ongoing surveys. We have 5,000 at the moment, plus another 10,000 that are unconfirmed but have very high probability of being correct and real. So that's a total of about 15,000. And the best guesses are that within a decade we could have 100 or 200,000 exoplanets. So the numbers have been going up almost exponentially, and that will probably continue for a while. But just having larger numbers is not going to answer some of the profound questions we're worrying about, which of course are how often are there habitable exoplanets and do they have life on them? Those are very hard experiments compared to just finding more exoplanets. And they're the experiments that are consuming astronomers in the next 5 to 10 years using ground-based telescopes, big new ones, and the James Webb where it can help.
All right. And then we have a follow-up question from Eudora that regarding the exoplanet research, but also kind of going back to the why do we always study the universe in its past? What if these exoplanets or other things that we're studying don't exist anymore since we are looking into the past to see them?
So that's not a real concern with exoplanets because almost all of them are in our backyard, essentially. Kepler's satellite, NASA's Kepler satellite, found still about 2/3 of the known exoplanets. and almost all of them are hundreds to a few thousand light years away. Well, the Milky Way is 100,000 light years across, so they're in a very much in our backyard, a small fraction of the galaxy. And since they're hundreds or thousands of light years away, we're seeing them as they were hundreds, centuries or millennia ago. And that's not very long in the history of a planet. So we don't see exoplanets far enough away for light travel time to really amount to very much.
Gotcha. All right. Next question is from Ghost 180. They were wondering, if we were contacted by aliens, do you think it would be more likely for them to be alien organisms or alien artificial intelligence?
Well, that's an interesting question or speculation. People who think about this, philosophers as well as astronomers, do wonder if artificial intelligences in general might dominate the universe, because once a biological creature develops the ability to become a machine or a computer, then essentially their longevity is infinite. And so statistically, if a number of biological organisms have gone through that membrane, if you like, to machine intelligence or AI, then they're eternal and they will dominate the statistics. We haven't made contact with anyone yet, but certainly people have made a logical argument that most of what's out there that we might make contact with will be machines or robots or AIs rather than biological entities.
All right. Raja Nano was wondering, going back to exoplanets, what is the importance or significance of characterizing exoplanets when we find them?
I think the importance is we want to know what happens on these worlds, because we've now found over 5,000 exoplanets and hundreds are habitable in terms of being the right distance from their star to have liquid water on the surface. But we still don't know what the atmospheres of most exoplanets are. We don't know about their geology. We don't know whether they have continents and oceans. So we know very little about them. Almost all of these exoplanets are characterized by one or two numbers, their radius and their mass. And sometimes you have both, and then you get their mean density, but that's it. So characterizing exoplanets is really the next stage of the research, because we know so little about almost all of these thousands of exoplanets. And that is hard work. That's going to take bigger telescopes, very difficult techniques that are now possible in principle, but we haven't yet been able to inspect the surface of an exoplanet. We've only sniffed the atmospheres of about a dozen out of 5,000. So it is very early days for characterizing exoplanets.
All right. The next question is from Dysonaut. Would it be possible to transfer electrical energy through microwaves from the moon down to Earth? Like taking that energy generated on the moon and sending it to Earth?
Certainly. So we have the ability to beam microwave radiation through space. Certainly it doesn't get scattered or deflected or dissipated. So that's always been a thought, that we might be able to create sun power, solar power in space, and then beam it down to the Earth to fuel our civilization. And we could easily do the same thing from the moon. So this is part of the vision for a moon base, for example, is to have huge power generation there, and then to beam power transmission is one of the most important things on the Earth as well as in space. And so this ability to beam microwave energy in a very dense, highly efficient way is certainly possible, but the technology exists to do that.
All right. Next question is from Prab. As the discovery of new exoplanets as the number of exoplanets that we found is growing continuously, is there any chance that we would find a new natural element beyond what's on the periodic table now, if we ever, got to these planets or in their spectra or something?
It's a possibility, so it's worth considering. But the history of astronomy suggests otherwise, because we've been doing spectroscopy, which is a tool that lets you see what chemical elements are, especially in gas nebulas and stars. Those are the common objects we've done this for. And we've been doing this spectroscopy for 150 years, and with big telescopes significant telescopes for a century. And nobody has ever found in a spectroscopic signature of an element that's not in the periodic table. But we've seen traces of all the elements in the periodic table out through space and in various nebulae and stars. So I think the history suggests that there are no elements left to discover. And there's no particular reason that exoplanets should harbor new elements that we wouldn't find in other locations like nebulae or stars.
All right. Next question is from WW Crest. So do you think the manned Artemis mission that's coming up is going to cause a big jump in the younger generation getting into astronomy-related jobs in the way that the Apollo missions kind of did?
I don't think Artemis is going to be a game changer the way Apollo was. Apollo was a sort of singular success story of an incredibly difficult technological challenge laid down by John Kennedy, young president, in 1963, I think, to get to the moon by the end of the decade. And, using technology that was fairly primitive. There was no internet. There were no cell phones. Computers were huge back then. There were no PCs. So, it captured people's imagination just because it was such a difficult and amazing thing to have done. Going back to the moon is obviously not as spectacular and exciting and novel as going there the first time. And, I'd rather be more optimistic, but I have a feeling it's not going to capture the imagination quite the same way. The one big difference, however, is that the Apollo, Mercury, and Gemini astronauts were overwhelmingly white men, and diversity is now built into the astronaut corps in a way that it never was. So the good thing about the Artemis missions, and we've already seen this in the selection of the Artemis II crew, is that the people who are going to go to the moon the second time will start to look more like the humans generally than one small subset of humans.
All right. Rajat Nano had a follow-up to the question before about the idea of bringing electricity from the moon to Earth. They were wondering if this ability would mean that we would see wireless electricity here on Earth in the future.
Well, we can see wireless electricity. Those mechanisms exist now. Wireless power generation is possible. Induction power generation, generating power by movement, is possible. There are various clever ways of generating power. And of course, we don't have to go to the moon to generate substantial amounts of power. The solar kilowatt hits every square meter of the Earth uniformly, and we just need to capture it in places where there are not a lot of clouds or in the daylight hours. The only thing you gain from the moon is there's no atmosphere, and you could have a permanently lit place, so you get an efficiency factor there. But basically, all the power generation tools that we could use on the moon, we already have accessible to us on the Earth.
All right. More moon to Earth questions here from Pandora Light. They were asking, so the space industry is doing a lot to go back to the moon in the early future and is planning to build some sort of permanent bases there. But their question is, can we mine energy maybe not energy, but mine elements, I think they mean, because they asked helium or something else on the moon and transport it to Earth?
We can definitely mine the moon and bring those ingredients back to the Earth. The element you're probably thinking of is helium-3, an isotope of helium that's a vital component in nuclear power generation if you ever want fusion to work. So helium-3 is a valuable commodity on the Earth, and it's actually very rare on the Earth, whereas it's produced by natural irradiation of the lunar surface. And so the helium-3 on the moon is a substance that really doesn't exist much on the Earth, or is very rare and expensive. That's something that probably is worth transporting back to the Earth. But otherwise, lunar geology is not really dramatically different from terrestrial geology, so it's hard to imagine it being worth the cost of transporting ores of various chemicals, whether metals or rare earths, things that are valuable to our industry, when we still have plenty of those available on the Earth.
All right. We have a question from Yang next, and I think it's kind of a more high-level question, so I'm going to simplify it a little bit. Hopefully, I get the idea across. They were talking about the pillars of creation and what's happening there, and I feel like it's a something that a lot of people have seen, but they were wondering about like what is going on in the pillars of creation. Is there like supernovae like things happening there? Is there dark matter objects forming? Are there other like when we look at the pillars of creation, like what are we looking at exactly?
So the pillars of creation is a very well-known, iconic image from the Hubble Space Telescope, going back 15 or 18 years now. I don't remember what year it was released. And the true color version of it is very evocative. And it's these towering columns of gas and dust where there are stars embedded in them, and then particularly at the top of the columns or the bottom, since there's no up or down in space. So what's going on is these are nebulae. These are glowing regions of gas illuminated and irradiated by stars nearby or stars forming within them. And the stars that you see at the edges of the pillars are actually ablating the gas. So these young stars have intense ultraviolet radiation and solar winds, and these solar winds are sort of eating away at the gas at the top of the column. And so we're sort of seeing that process. And in the meantime, of course, they do illuminate or energize the gas. And so it glows very hot in hydrogen, which colors the gas pink, and then in oxygen, which colors it green. And so those are the colors you see in that image.
All right. Next question is from Lauren Sekar. They have a follow-up to the black hole, some of the black hole questions from before. So if black holes are high entropy objects, does that mean they absorb entropy from objects falling into them? And do they reduce the entropy in their area of space?
I mean, entropy is a quantity that is fungible at some level. It can change, it can convert as objects change. But basically, an object that falls into a black hole contributes mass and entropy. And so, yes, it affects the entropy of a black hole when something falls in. The high entropy, though, of a black hole is really associated with the fact that is a very high density form of matter, and so there are many possible states that matter could have beyond the event horizon. So as you grow a black hole, its entropy grows, and its entropy is actually proportional to the surface area of the black hole. And so bigger black holes have bigger entropy proportional to their surface area.
All right. Next question is from Lying Lion 88. If there is the possibility that there's extraterrestrial life, would they undergo the same type of evolutionary process that we've seen on Earth, or would it be very different? And would it depend on where they are in their quote like Goldilocks area or the habitable zone?
So that's an important thing we want to know about life in the universe, apart from being able to detect it for the first time. We sort of want to know whether the rules that govern evolution and biology on the Earth apply beyond the Earth. Are these universal? Is biology universal? Are replicating molecules, the DNA and RNA, that is the information coding molecule of life on Earth, is that universal? And on the larger scheme of organisms and evolution, is natural selection, Darwin's theory, is that universal? Because we don't know, and it might not be. There's a reason to think that it should be or could be, which is that life anywhere, regardless of its fundamental microscopic composition, is going to exist in an environment. And for life to persist and adapt and survive in that environment, it will have to react to that environment. And that is essentially the sculpting of organisms by the natural environment and their selection by their fitness for success and propagating and persisting is natural selection. And so it's reasonable to imagine that some process like that will occur on any planetary environment, but we don't know. So it's just a speculation for now.
All right. And speaking of extraterrestrial life, Dysonaut is asking, why haven't we found any? Why haven't we found any alien life, even though there are these components of life nearly everywhere? We found water and planets with atmospheres and things like that?
I think we haven't found life so far because it's a very difficult experiment. So I would not view the fact that we haven't found life beyond Earth to be indicative of the fact that it's rare or doesn't exist. I don't think we could draw that conclusion yet, because we know so little about many of the exoplanets we found, most of them. Even the ones we think are habitable, we still only know their mass, their size, their surface temperature. We don't even usually know their atmospheric composition. So I think that's the answer to the question, is that the game is too young. We haven't been doing this long enough or carefully enough. So it takes a lot of data and difficult to obtain data to characterize an exoplanet in terms of its biology. This is something we're barely able to do and will be able to do in the next decade. So I think the jury is out basically on the existence of life elsewhere or its abundance until we can do these difficult experiments.
All right. And it is 10:55, so I think if this works for you, Chris, maybe 2 more questions
Sure.
for today.
Sure.
So Rajat Nano was wondering if you could please comment on ESA's JUICE mission that launched, I believe, a week ago or maybe 2 weeks ago. That's off to Jupiter.
Right. Icy Moons mission of the European Space Agency. It's a very important mission. It's going to take a while, a good part of a decade, to get to its destination and start doing its work. So the Icy Moons of Jupiter mission is going to target particularly Europa, which is a compelling target because of its subsurface oceans. We'd love to know more about Europa. And this mission is also going to go into an orbit of Ganymede, which is the largest moon of Jupiter, which almost certainly has a subsurface ocean under a rock and ice cap. And that'll be the first space mission ever to go in orbit around a moon of a planet anywhere, except for the moon itself. So that's a very exciting thing. And it will, of course, therefore be there for some few years, and will be able to make detailed measurements and mapping and radar of the surface. So this is a pretty sophisticated mission with about a dozen instruments on board that's going to spend years looking at 2 in particular, and then at least from a larger distance, a couple more of Jupiter's moons that could potentially host life. It's not a pure life detection experiment. It's important to be clear about that. But it's going to characterize the habitability of these moons to a degree we've never been able to do before.
All right. And last question for today is from Polycythemia. They were wondering, after the James Webb Telescope, which is funny because, we're still very much in the era of JWST, but looking forward, what is the next telescope in the making? What's going to be its successor, or maybe not direct successor, but other big space telescopes that are coming up? So
the limitation of the James Webb in part is just because of its field of view. The James Webb looks very deep, but it looks at very small patches of sky. That's a function of its optics and the size of the detectors. So the James Webb is not really good for surveying. It's just good for making measurements of particular objects in small. It can do very deep surveys of small patches of sky. There's a mission that was originally called, the acronym was WFIRST, and it's had some name changes since then. But it's the idea of sending up a substantial sized telescope that would have a very wide field, and it would be an optical telescope. James Webb is mostly near infrared. And that would be an amazing survey telescope. Hubble also cannot do real wide field surveys. So we've never had a wide field survey telescope in space. And that's the one that people have their eyes on now. To do it from space gives you advantages over the ground. You can measure ultraviolet radiation that doesn't reach the ground. Your image quality is perfect because there's no atmosphere, and the sky is incredibly dark, so you can go deep. So that's the mission people have their eyes on, and the time frame for that now is the mid-2030s, almost up to 2040. So it does take a long time to fund and launch missions like this that are beyond the current mission, because James Webb could well last 10 or 15 years. So thanks for all those questions, covering a lot of ground. Interesting as always. Thanks to Vicki for running the session. And I think we have one on the books I have a trip coming up to the Czech Republic. And then I think in 2 weeks, we have another session planned.
Yes, I think right now we have it scheduled for May 9th, which is Tuesday at same time as this one, but it'll be over on our YouTube channel, Astronomy State of the Art. And yeah, thank you guys all so much for joining us today. Thank you to the people who followed and our first-time chatters for coming by. And we will see you folks next time. Bye.